Hi team, welcome to Wiggins Maths. In this video we're going to be looking at the Newton-Raphson method for iteration. So this was an iterative approach invented by Sir Isaac Newton and Joseph Raphson, and you are given the formula in the formula book, and it is as such. Okay, so what it is that the next answer is produced by the previous result, subtract f of the previous result divided by the differential of the previous result. And what this is in fact doing is it's using the tangents on the curves to get closer and closer and closer to a root until the tangent eventually intersects the x-axis at the root that we would like. So each time you do the iteration, it's creating a tangent that is closer and closer and closer to the root of the function. Now what that actually means is, when we take our initial guesses, which is what we have to do with an iteration, have a think about why choosing the turning point as your initial guess would be a terrible, terrible idea. It's simply because the tangent to a turning point is a flat horizontal line, right? So therefore it's never going to get to the root, because the tangent will always keep producing the same tangent, which is just a horizontal line. It's also worth pointing out, if you choose something that's close to a turning point but isn't the turning point, it will eventually get you to the root, but it may take a very, very long time. So we have to be very, very careful as to what we choose, but luckily in the exam we are often told what our initial guess is. Okay, so let's have a look at this one then. So here's our function, and we would like to have a look at finding an approximation to alpha by applying the Newton-Raphson approximation once to get our second approximation. Also worth pointing out that a question, it might say, why should we not use the point A as our initial guess? That's because it's a turning point, and that will produce a tangent which will not get close to the root at all. So let's do this methodically. So the first thing we're going to do is we're going to write down f of x in a slightly more useful format. Some of you may notice, but I would be required probably to write it like this instead. Okay, I'm also now going to make sure I work out f of 1.2. And f of 1.2, when I type into my calculator very, very carefully, I'm going to write out my full calculated display. So I get negative 0.07337891442. Okay, next thing I'm going to do is I'm going to differentiate that function. So 3 over 2 x to the power of a half, add e to the negative x, subtract a half x to the negative 3 over 2, and that becomes 0. I'm now going to substitute in 1.2 into the differential, and when I type it into my calculator, again very, very, very carefully, I get 1.563998997. Okay, so now I'm in a position to work out what x1 is. x1 is equal to 1.2 subtract negative 0.073 blah 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 over 1.563 blah blah blah. And when I type this into my calculator, I get 1.247179. It requires it to 3 decimal places. So that is 1.247 to 3dp. So as you can see, it's not far away from 1.2, but it's a slightly better approximation. And then if we were to use that again to find a third approximation, it would be even closer still. Okay, so that's it really. So remember, watching this video doesn't mean you'll instantly be able to use the Newton-Raphson method. Practice is the key to success, and the more you practice, the better you will become. And of course, amateurs call it genius, masters call it practice.